Okay, hello everyone. Hello to everybody in the chat room. I've seen a lot of people here today for Felipe. So Felipe, I guess it's for a lot of us, it's a person that doesn't need an introduction. But for those who's new to our community, Felipe is a machine learning research scientist at Layer 6 AI. Um, he has led team. He led team to lab that achieved made a good achievement on a lot of the competitions in the academic research field. So without further ado, today Felipe is gonna give us an introduction on recommender system. Okay, Felipe, it's all yours.
Okay. Hello, everyone. Thanks a lot for the introduction. So first of all, welcome. So we are thinking about creating this recommender systems workshop. It will be a really short workshop focusing in some like relatively easy to medium difficulty, but is supposed to cover different levels. Different levels of different sets of problems that appear in the industry when you're actually trying to create these things. So in order to do that, first, let me introduce the team that is going to work with us. So myself, I'm a machine learning research scientist at Layer 6. So we are the research branch of TD. We have Ella Shen, that she's a machine learning engineer at Drop. We have Serena McDonald, that she's a senior data scientist at Delphia. And we have Werner Shaw, that he's a data scientist at Scotiabank. So I will be the one conducting most of the course, but Ella, Serena, and Werner will be helping me out and answering questions and helping with the code and the design of all the project. So what are we going to learn? So the course is roughly divided into 9 hours, and we're going to touch obviously what recommender systems are, the different kinds of recommender systems. We're also going to check the basic ways to evaluate a recommender system, but maybe more important, we're going to touch on ranking. Ranking is extremely difficult thing to do when you have recommendations. We'll talk more about that in a second. Finally, in the last class, we will talk about how deep learning shows in recommender systems. It's actually extremely surprising, but deep learning is not as helpful as people think for recommender systems. There are many papers on deep learning associated to recommender systems, but it's only a handful that are actually usable, either because of scaling problems or because the results that had been shown on the papers are not replicable. As an example of that, I strongly suggest that you read the best paper of the recommender systems conference of this year, and they explain how difficult it is actually to replicate the results that exist for recommender systems. So as the theory is not that particularly deep in every direction, we are going to have a lot of hands-on interactions. There will be a set of small coding questions where you have to interact with the data, create a small setup for one of the techniques, and so on. This will help you understand the main difficulties of recommender system, that is basically scaling, speed up, creating, going through these ideas for 10, 100 products, 100 items is particularly easy, but once you go to millions, things begin being quite complicated. So we will focus a lot of that on at least to show where the problems arise. Because of the resources that we're going to use for the workshop, we are not going to scale, but I will definitely be telling you how you can do it in your own time or with your own resources. So what is a recommender system and why do we care about recommender systems? So a recommender system comes naturally from a business interaction with an user. The business, in one sense, have a bunch of items that they want to recommend to they want to sell. But the user is trying to figure out okay, so I have to choose from some of the items, but you cannot recommend every item, because if you have 100, then the user gets overwhelmed. It's like being in a restaurant. If your menu is really large, you sometimes take a long time to make a decision. But if your menu only has 5 things and you really like 3 of those, then your life gets much easier. So from the user's perspective, it will be really nice if we could tailor the recommendations to the user and the particular circumstances that the user has. So we would like to understand the user behavior and predict this desired needs and patterns. Think it, for example, there is a huge difference between like if you're booking to go to any place, like you don't want all the hotels. You have filters that help you narrow down the exact criteria that you're looking for. And those filters sometimes correspond to your needs, corresponds to your desires. But some of those needs and desires can be read by the user behavior, what you have done before, in order to better tailor the recommendations for that user. From the business inside, like the business is actually one of the reasons why recommender systems is so difficult. Recommending products sounds really simple, but once you begin to put business rules, like for example, you are overstock on something, or you are getting a sale for certain products, so you want to push those products, or you want to freeze on a space, or whatever. There are many business reasons why you may want to tailor certain products. So the question is, like, from a fixed set of products or a fixed set of business rules, how do you interact with the users? What kind of things would you recommend to the users? Also, coming back, the business wants to personalize, because every time that you personalize, the business will feel that they have a closer connection, or the user will feel that the business know him better and therefore can understand the needs or the wants they have better. So that's the why and what. But like, this is really easy to say, much more difficult to do. But the idea is, actually, most recommender systems are based in a really, really simple idea. That is basically collaborative filtering. What is the idea of collaborative filtering? You have two characters. In this case, we have Homer Simpson and Peter Griffin. You know that Homer likes pizza and he likes donuts. You know that Peter Griffin likes pizza and he likes donuts. So if Homer also likes, I think that's fries, it will be nice to know, it will be a good idea to recommend fries to Peter. Why? Because we had already found that Peter and Homer are similar people. Therefore, we suspect that whatever one likes, the other one will like as well. This sounds totally reasonable. This is perfectly fine, but there is a huge problem. First, and probably the most interesting one, is like, what does similar mean? How can we describe customers that are similar? Like, and are we doing it in the right way? Like, should, like, for example, like the old kind of recommender systems will, and many of the actual and the current recommender systems, they will take a lot of demographics and use those demographics in order to find similar people and recommend to one, like what they found that is a generic in certain clusters of population. This gets tricky, and sometimes it leads to really bad things happening, especially in the grocery industry or like in the supermarket industry. Bad recommendations, bad tailoring have made people feel that they don't know them at all. And it will be easier to solve that if you have a better recommender system that understands the users just from the data and not from some checkboxes that they are filling in when they are signing up for X or Y stuff. So how does this work? In general, you will have some sort of matrix that represents, it's called the user item matrix, that collects either implicit or explicit rankings that the users have to products. Let me give you an example. Like, for example, every time that you click on Amazon, you can think that, like, oh, that's something that the customer may have liked. If you buy it, then you can actually increase the likeness. For all the things that that sort of implicit is your behavior has made the system believe. Sorry, like, I'm going to stop this for a second because I keep getting Slack messages, but I don't think it's from this group. Is that correct? Yeah. Okay, sorry about that. So you have the implicit feedback that is something that you are collecting from the user as he's moving or he's working on a website, or that things that they had bought, or just the history of the user, but they have never actually rated anything. The explicit kind of feedback or the explicit ranking comes when the user actually rates. And for example, if you remember, in Netflix, there used to be a star system. IMDb also has like some sort of a star system. Amazon has a star system. Hotels.com, all of them is places where you can actually rate the hotels, the movies, the items, and those ratings can be put into the matrix. But if you think about it, places, any of these companies, they have like millions of items, and nobody has interacted with all the items. So most of these things are unknown. Most of these ratings are unknown. And actually, in most cases, it will be less than 1% of the all possible interactions that will be known. So this creates a really huge sparse problem. And just to give you some order of magnitude, this matrix, if you consider it as a sparse matrix to save it, and you have 1 million customers and 1 million items, it will be more than a terabyte if you were to write it as a dense matrix, and it will be just less than 1 gigabyte if you're going to write it as a sparse matrix. 1 terabyte of data is too much, especially if that is like if you need to process this data or do something with this data, you'll make it unfeasible, and that's where the scaling problems begin to happen. Okay, so then the question remains, how can we describe customers that are similar? The easiest way is, okay, if two people have rated implicit or explicit similar items in the same way, you will think that those customers are similar. It's a simple idea. Basically, I'm going to think people are similar according to what they have done before. And I'm going to use that as my measure of similarity. That's the most basic approach, and that's basically what is known as memory-based collaborative filtering. So that works really well. It's just a measure of similarity. You can use many measures of similarity as distance functions. The one that works the best is some sort of normalized cosine similarity, but we'll talk more about that during the course. Now, a much better approach has to do with using matrix factorization. If you think that matrix is huge. It has 1 million by 1 million parameters or possible entries, for example. But you can always factorize that matrix using matrix factorization into two collections of vectors, one representing users and the other one representing items. So if you were able to do that, then you can encode and you can find like the vector representations of users will be now given by the vectors that are in the matrix associated with users, which will be great because now you can use those in order to compare them against each other. So here is another scaling problem question. Suppose that you have 1 million users or you have n users. You want to compare which ones are similar to each other. So you have some measure of similarity. How many times, if you want to recommend to every single user, you want to recommend something that other user has seen, you need to compute all the pairwise distances between these users. But that's an n-squared problem. So this is actually increasing the nearest neighbors increases with the number of users in a square way, which is terrible because like the square is already really bad for big data. There are techniques to solve this problem, and one of the most common ones is approximated nearest neighbors. And that's something we will touch briefly, but like if you want to see a nice implementation that I particularly like, is called Annoy. It's the Annoy library by Spotify, where they basically use some hashing of certain regions in order to determine what things are closer to each other to a high degree of approximation. But that's by far not the only one, and there are many, many others. There is some implementations that are already written for Spark and things like that. So going back to matrix factorization, you are just going to factor this huge matrix into user and items. Luckily, there are techniques to do this factorization for a ratings matrix that is sparse that are relatively easy to do. Among those techniques that there exist for factorizing this, let me see. Among those techniques, the one that is probably the most important is called alternating least squares. That it will take that loss function or similar loss functions, because the loss function, as you see it right there, is not the best loss function. Usually you want to put some regularization for this, because if you count the number of free parameters towards the number of entries, this will be really easy to overfit. But so you need to regularize it somewhere. how, but like we'll talk more about that later. In the loss function, alternating least squares is just going to update to minimize the loss function, thinking of u and v as independent. So first, in the first step, you're going to minimize for u. In the second step, you're going to minimize for v. Then you're going to minimize for u again, and so on. And you repeat that process. That's basically called alternating least squares and has really nice convergent properties, and it works like a charm. So we'll implement that. We'll talk about the benefits of it. We'll talk about how to use those results and how to validate our results during the course. So that's model-based collaborative filtering. So notice the difference. Like here, you're learning some embeddings. Meanwhile, in the previous one, you didn't learn anything. That's the difference between memory-based and model-based collaborative filtering. Okay, so that's good, no problem. Now, let's talk a little bit about our second class, that is basically ranking. So suppose now that we know how to recommend products using any of this collaborative filtering stuff, but we are not like perfect, and we know that if we sort of recommend more than one item, we probably will do better in terms of revenue. The more we recommend and the more they click, the more they buy, then the more revenue I'm going to have. So like, how do I make sure that I can give a list of recommendations and that they are sorted in such a way that the top one is the one closest to the user, the one that is more relevant to the user, and when the bottom ones, maybe the user like them, but not as much. This becomes tricky, and we need to begin thinking about how the user is acting. So the user starts by basically making a query. He's saying like, I want a TV, I want a trip to Hawaii, I want whatever. I have information from the user, I have the query information, and I have all my items and the features associated with those items. I can use all this information in order to create a really good list that corresponds only to that query and to the user. So I'm giving personalization, and not only personalization for the user, but like explicitly for the query. And I'm giving a list of things. How do I evaluate that the results that I'm giving are good or bad? There are many ways, and sometimes it depends, because if you think like, for example, how Google works, when you look for something in Google, there are many options that actually work. So sometimes you have many good options, sometimes you only have one option, and that creates two different ways of measuring the quality of your ranking. The one that has to do with many documents is, or the one that I like in that direction, is called mean average precision. This is a really clever way of computing, but the problem of mean average precision is that it's a kind of a little slow to compute, but I haven't been able to go around that problem for a while. But it's a really good measure of knowing how good your retrieval of the query is doing. And there is another one that is really common, and that was the one we were using in the competition, the RecSys competition this year, that is called mean reciprocal rank. That usually is used when you think that there's only one answer that was what the person wanted. You sort of make an assumption in that direction, or that the one that matters is only the one that was relevant, that was at the top. Both of those metrics will lead to different things, but we'll talk about ranking in the course. But more important, we were going to talk about something that many times is not touched. That is, how do you create features for these kind of problems? So we're going to use the same data set that we use in the RecSys competition, and we're going to approach the creating features part and what are the drawbacks or the benefits of certain kinds of features. We'll find out that the item to items interactions, item to users, there are local features, there are global features. There's a lot to be said about how to create features that will better create rankings. And also, we're going to talk about the different loss functions and training mechanisms associated with ranking. The most common one associated to ranking is called pairwise. Basically, you're always going to compare two items, and you're going to rank them according to that comparison. What you will find out is that sometimes that's not the best approach. You can also use something called points-wise ranking, that you are just going to rank one item at a time. And that gives, like, at least in our experience, and in some cases, it can give better results than even pairwise. Finally, So this is what I was telling you about ranking. Finally, we're going to talk a little bit about deep learning. So in deep learning, there are many approaches. You can read, for example, there was one that was called deep matrix factorization. People have used transformers. There is a lot of stuff that people have tried to do with deep learning for recommenders, and many papers claim excellent results. But in our experience, that's not usually the case. The two things that I have tried personally and I had found consistently good performance are node to back. That is a way of embedding items or users in finding some latent representations that you can then use to do inference. And it basically works in a similar way as word to back does. You sort of create your graph according to the information that you have from the ratings or from the users or whatever, and then you do random walks associated to the graph. You use those random walks in order to generate sentences like objects, and then you're just going to use the same idea as word to back in order to generate embeddings associated to each of the items. This is a really powerful technique that I enjoy a lot. Um, that's one of them. The second one that I particularly like as well has to do with variational autoencoders. So many times the information that you have in your, especially when you have implicit feedback or implicit ratings, is that you can translate, you can encode that information in a latent space, a much lower dimensional latent space. That's the autoencoder part. But if you use variational autoencoder, you may have the chance even to generate fake users, to generate fake data to some extent that you can then use to better tune your your other models. Notice that these two techniques have something in common, and the thing is, like, I'm not going to be looking for an end-to-end solution, because end-to-end solutions in recommenders, I haven't found anything that works. What I'm going to find is representations for either items or users that will better help me train different models. You will also find, like, for example, one thing that we also find is that using XGBoost or using linear regression or using like a simple transformer encoded architecture can give you the performance that you want as long as you know how to normalize the data. You still need to create your features. You need to create many, many features. You need to normalize it. And once you normalize those features, you can train and go ahead. But in general, deep learning hasn't, in my experience, hasn't shown to be that great at recommender systems. So yeah, so that's basically the summary or the main ideas of what we're going to cover. The first class will be the basic techniques, collaborative filtering, finishing with alternating least squares or weighted alternating least squares. We're going to code those things. We're going to talk about the problems that exist. Then we're going to move to ranking. We will spend talking about the metrics associated with rankings and how to create features for these kind of problems and the problems that comes with scaling. And in the last session, we're just going to talk about the deep learning approaches, basically node to back and using multivariational autoencoder for recommendation. And I think that's it. And if you have any questions, please let me know. Thanks. About the deep learning approaches, basically node to back and using multivariational autoencoder.
All right. It was thanks Felipe for a great introduction. We have a Jerry asked a question. We have a question from the chat room. But before we get into the questions, I just want to remind people that there is a special discount code, which is the word launch. If you apply this discount code, you will get 30% discount within the next 48 hours. And if you are ACE member, if you log to our member area, each one of you should have a specialized discount code. And based on your participation and various involvement in the ACE community, you get a different discount. So make sure to check that out. Okay, so let's get to the question. So the question is from Jiri. Jiri says, "Hi Felipe, D hat about discounted cumulative gain. What is the advantage or disadvantage of this performance measurement? Thanks."
So that's actually like there are several metrics associated with evaluating a recommender system. I don't like the advantages or disadvantages counts with the kind of problem that you're working with. Like for example, if you think on, I'm just going to talk about these two because like if I go to the discount cumulative gain, it will be much more complicated. But like if you consider like for example MRR against map works really well if you have many possible positive outcomes. Meanwhile, MRR works really well if you only have one. But this is just a metric. This is just a way of measuring. It's just a metric. Let me give you a particular example. If you're looking for the definition of a sentence, then you will have many websites will give you a good definition, and that's okay. You can go through many websites, but sometimes if you only care about like what the customer bought, the customer only buys one thing, and having that on the top will be better. So MRR will work better on that case. So it really depends on what business problem you have. Will guide you about which metric to use. We can also talk about the normalized discounted cumulative gain during class, but it's just dependent of the business inside that you have.
Okay. Christopher has a question. Would there be any focus on time-sensitive recommendations? I think he's referring to the workshop. For example, if I want to recommend live TV content and account for what and the order of a user was watching content.
So accounting for order is actually a really good signal. Like most of the times, historical signals can help you a lot into being able to predict what the user is going to like next. Like we are definitely going to touch into those things in the feature creation because we are going to use the same data set that we use for RecSys. And for example, our team, we use several historical like features. And if we look at the solutions of other teams, and we also saw that they use those features. What we also find out is that is again problem dependent. For certain problems, long history is helpful. In our case, for our models, we found that it doesn't matter what the person like was doing like 6 months ago or like the previous 20 interactions that they have. Usually what it mattered was the last two. So like there's historical information that is useful, but it really depends on the problem. And sometimes it's a good idea to summarize that history somehow, but some other times it's just enough to take the last two events in the history. But we're definitely going to talk about that in feature generation.
Okay, here's another question from Chris. How often are you defining custom loss functions for training ranking algorithms?
You mean in my work, or
how often are you defining? I think he's referring to like in general, like the general practice, or when you're working it.
So not as often as you will think. Most of like there is a, I think like the most common loss functions will be like at most 15, 20. Most people actually only uses like 3 or 4. And most people use really well designed and implemented algorithms. What will make the difference in performance will be feature generation. And that's where you iterate the most often.
Okay, that makes total sense. Okay, Pensive has a question. Could you use a transformer to learn what history is useful?
Yes, we actually did. Well, we didn't do that with history, but the short answer is yes. The transformer has an advantage of being able to learn certain things about history, but in a really particular way. So the transformer basically works by doing self-similarity between different, like if you put it in a historical context, between different items in history. So that can be good and bad, because it can be good because the different heads will create different groups where you will compare those groups and get signal about similarity between those two groups within the history. But the question is about relevance. Like further back in time, information sometimes is not relevant, so it may just have too much noise. So transformer architecture is still being tested in the recommender space. We use it in some sort of historical event as if we were assuming that a person was scrolling, and it worked really well. But the thing that worked the best was SGBoost.
Hmm.
But you can always encode historical information, either from transformer, from SGBoost, or from the data itself.
Hmm. Okay. Um, I think that's about all the questions people have. So um, I think we're still very good on time. So we'll probably um, wrap this up early. And so those in the chat room, if you still have any questions, and this is the opportunity to ask Felipe.
Yeah.
Otherwise,
So welcome to send me an email or contact me directly. Like I'm perfectly happy talking with anyone.
okay, great. If you have any questions, feel free to send Felipe and then or send us a message. Um, okay, Matter has a question about the workshop. Are you going to cover something on spurious recommendations also?
No, no, I don't think I'm going to touch that topic. I actually don't know what that is.
Okay, I think spurious. I think Serena did a video a while back. It's okay. There's a 5 minute video that explains what spurious recommendation is. I can't pull that off the top of my head, but um, so for those who don't know what concept, you can check it out. Um, okay, so looks like that's all the questions we have right now. So as a reminder, discount code launch valid within the next 48 hours. And if you have still, haven't checked out the workshop recommended page. There's a lot of information. In the meantime, I do have a question, which is the prerequisites of the recommender workshop. So, is there anything that people need to know before they take the recommender, before they go to day one of the class?
Yes, I mean, like, I would recommend that you read a little bit about the topic beforehand. In terms of programming, I will expect people to know how to code because, like, um, you should know the basics of Python at least in order to be able to do these things. If you really want to scale them, Python won't be enough. If you are thinking about actually putting this in production, you will get more advantage for implementing in your own time the version of similar things either in C++, Java, Spark, or any of like more like challenging kind of languages. Um, but that's if you plan on putting it in production. If you just want to get the ideas and the feeling of how everything is, a basic understanding in Python and machine learning pipelines should be enough.
Okay. Here's another question from Chris. Are you going to cover making novel recommendations as opposed to obvious? For example, all books from same author versus similar genre books, different authors.
That's an excellent question. So we can definitely talk a little bit about it, and I'll definitely will mention it. I haven't created anything particularly designed for that, but sometimes also that comes with some business rules. So let me give you a simple, like, there is something that is called content based recommendations that basically you're going to look at the features that are associated to the items, and then associated to those features you are going to create some similarity between the items. It's quite similar to what I had been talking about. But suppose that you want to explore a little bit. So you may try not to recommend just the closest item, but maybe the fifth closest item. You may want just to create embeddings or give features that is this belongs to a different category. This the the thing about being able to recommend things that are totally new will be is particularly useful when you have users that buy among different range of things. Like that's why you get in Amazon things like customers who bought this also bought this other thing. So you can also get that a little bit of that with user behavior, but it is a difficult question.
Okay. Um, so we will cover techniques for dealing with the long tail problem.
With long tail problem, you mean like in what sense?
I'm not sure, but if I have to guess, I think he was referring to the long tail items that are not very popular.
So yes, I mean like that's the typical way that is dealt with has to do with dealing with bias, at least in the memory-based recommender systems. You can always deal with bias and simplify and get better recommendations for these long kind of tails. But in general, that's also a difficult question, as it is the question in general of cold start problem. What do you do? What do you recommend to a user that is completely new? How do you recommend a product that is totally new? Those are those are really difficult, and I don't think nobody has a great solution. There is a lot of heuristics about what to do, but there's no consensus of what works best.
So would be fair to say that your recommender system model is heavily dependent on the business objective. So
Definitely, that's always the case. Like different, like it will be not only in the business objective, but in the kind of business, in the like. But what all these things will guide is the feature generation. You will create features that will map to that particular kind of things.
okay. Um, so could you please copy the link of the workshop? Oh, okay. So it seems that I cannot copy and paste a random link to the